Power and energy are two sides of the same coin. Both are critical characteristics of modern computer systems.
Low power consumption was a critical advantage for CMOS when it was first introduced. This is the Radio Shack TRS-80 Model 100 portable computer. For many years, starting in 1983, it was the most popular computer in the world. It was also the first computer to use a CMOS processor. Because of CMOS, the TRS-80 Model 100 could run on 4 AA batteries, as compared to other portable computers that require to be plugged into the wall. Other microprocessors at the time used NMOS circuits for their logic. NMOS consumes more power than does CMOS. Here's one reason why. This shows an inverter made up of an enhancement transistor for the pull down and what's known as a depletion transistor for the pull up. The depletion mode transistor acts as a resistor. So when the enhancement mode transistor is on, there's a path from the VDD to the ground. That means that current flows even when the output is stable. That means that the NMOS logic gate is always burning power in this case.
Basic physics underlies the power consumption of the inverter.
Here's the RC circuit that we use to model the inverter. We know how much energy it takes to charge the capacitor. We integrate the charge over time and we get 1/2 CV squared. So if we plot the waveform, it looks something like this. Now, our math becomes easier if we consider both a charge and a discharge. In that case, the total energy for one cycle, 0 to 1 and then 1 back to 0, becomes the capacitance times VDD squared. That gets rid of the 1/2 factor. We've assumed so far that only one of the transistors is on at a time, but that's not always the case. There is a point during the transition at which both transistors are on. So current can flow from VDD to ground. That's known as a short circuit current. That short circuit current consumes power, but it doesn't help speed up the transition. But if the sum of the magnitudes of the threshold voltages of the pull-up and the pull-down transistor are less than the difference between the power supply and ground, then there is no short circuit current.
Delay and power consumption are related through the power supply voltage. Understanding this relationship gives us an important result.
Remember that power is energy per unit time. So given an operating frequency F for the circuit, the power consumption becomes F, the load capacitance, times the square of the power supply voltage. Total power consumption is the sum of the dynamic and static power consumptions. Static power consumption occurs even when no signals are changing in the logic. An important source of static power consumption is leakage. Modern transistors are imperfect and they leak current even when they're not on. The power consumption caused by leakage current is becoming a larger and larger component of total power as transistors get smaller. When we multiply together the speed of the circuit and its power consumption, we get an important metric, speed-power product. If we just concentrate on dynamic power consumption, we have a very simple formula. It's equal to the load capacitance times the square of the power supply voltage. So power consumption scales quadratically with power supply voltage. We can use a simple model to estimate the relationship between power supply voltage and delay. Let's use the effective resistance at the end of the saturation range of the transistor. That's just equal to the saturation voltage divided by the saturation current. This formula gives us an expression for that effective resistance as a function of power supply voltage. So we see that delay is proportional to 1 over the power supply voltage, which means that as we reduce the power supply voltage, power consumption goes down faster then we lose performance. We can use this information to help us manage power consumption, and we have two different cases depending on how much leakage we have in the circuit. When we have a relatively small proportion of leakage, when leakage is a small component of power consumption, we want to reduce the power supply voltage to the point that the circuit runs just fast enough to complete in the amount of time that we require. We call this strategy dynamic voltage and frequency scaling. By reducing the power supply voltage, we reduce the speed of the circuit, but we have a net win in speed power product. However, this doesn't work well when leakage values are high. In that case, we need a different strategy. We want to run as fast as possible and then shut off the logic. We can't always shut off 100% of the logic, so we may have a small amount of leakage in the idle period. But running as fast as we can allows us to shut off as much of the logic as we can in order to minimize leakage. This strategy is known as race to dark.
To review, dynamic power consumption comes from the charging and discharging of the inverter's load capacitance. Leakage current is another important source of power consumption. Power consumption is related to the square of the power supply voltage, but delay is related to the power supply voltage itself. We can use dynamic voltage and frequency scaling to optimize power consumption in low leakage environments. We use race to dark when leakage is high.